That's for you, that's not for me. That's not for me. I'm not going to do anything here tonight, so that's for him, that's not for me. Welcome, everyone, and I know some folks are still here taking seats. Good evening. My name is Andrew Aline, the Dean of the College of Science and Engineering here at the University of Minnesota, and I'd like to welcome you to what is the 17th Annual Misel Family Lecture presented by the William I. Fine Theoretical Physics Institute here at the University of Minnesota. We are greatly appreciative of the support from the Misel and Fine family, and just their timeless support of the university and theoretical physics here at the university, and for making an event like tonight here possible. And so I'd like to take the opportunity to recognize both families, Misel and Fine, for their support of us and this lecture. And if there are any members of the family here, if they could just sort of raise their hand. I think there's one. Okay. Thanks so much. Thanks so much. So the Fine Theoretical Physics Institute, it is actually a tremendous asset to physics at the global scale across the world, but certainly here at the University of Minnesota and to the state of Minnesota. I've come to appreciate all the different things that it does and the luminaries it brings to campus through my 2.5 years here as dean. We take a great deal of pride in the accomplishments of the faculty and researchers in the institute. Now, lectures like this Misel Family Lecture, are really important, not only for all of us to learn from these distinguished speakers, but to help motivate some of our younger students to hopefully look into a career in science and engineering and hopefully attend the University of Minnesota and really spark that interest. We're always looking for the best and brightest talent. This year, we saw nearly 1,700 new students enter the College of Science and Engineering, and many of these are going to be taught by folks that are part of the physics department, and if they're lucky, FTPI. We're really excited to see where they're going to go now and in the future. And we think we're off to a great start. And for those of you who were not aware, that number represents about a 10 to 15% increase in the number of students from last year, which was about a 10% increase in the number of students from the year before. So the College of Science and Engineering is definitely on an upward path. So enough about the college. You didn't come here to hear about that. You came here about quantum. Right? So I'd like to introduce the FTPI director, Alex Kamenev, who's going to tell you a little bit more about our distinguished speaker tonight. Alex?
Thank you, Dean Elena. Good evening, everybody. Thanks for coming tonight to be part of this new, very exciting development in physics. We're really glad to see all of you coming. I'm Alex Kamenev, Director of Fine Theoretical Physics Institute. Before I dive in, let me join Dean Elena in expressing my deep appreciation to Misel family and Fine family for their continuing support of fundamental science and public engagement in fundamental science. Our speaker today is Pablo Jarillo-Herrero. Sorry, Pablo, for butchering your name. I could never pronounce it properly. Pablo is a native of Valencia, Spain, and he got his undergraduate degree there, which followed by graduate degree at Delft University at Netherlands. After that, he moved to this country, and after a short postdoc at Columbia, he was recruited to MIT as an assistant professor then, and he stayed at MIT ever since. Pablo is, and his lab, are world-leading expert experts in field of two-dimensional materials, that is atomically thin layers of something. So the first of these materials was graphene, and that it will be a subject of today's talk. And Pablo will tell us about his groundbreaking discoveries in this field. And that will be followed by colloquium tomorrow at 3:30 at Tate Laboratory of Physics, and you're all welcome to join this colloquium as well. I hope you will do. Besides graphene, Pablo is famous in co-discovering and helping to understand our two-dimensional materials known as van der Waals materials. For example, he was the first to recognize that some of them can be, despite being atomically thin, can be very good magnets, which is sort of amazing observation. For his work, he received numerous awards, and they are listed in the booklet you have. And by the way, there is a questionnaire inside of the booklet, so please fill it out. We will greatly appreciate that. I will not list all of his awards. I will only mention 2020 Wolf Prize in Physics and 2020 Medal of Royal Spanish Physics Society, which I believe was presented by the Queen of Spain, Letizia. Is it right? All right. Some lesser known fact about Pablo is that he is head of house at MIT, which means that he, his wife Amber, and their 3 children live alongside 400 MIT undergraduates. And they share all their troubles and successes, and they help celebrate them, all their success. And they enjoy all fire alarms set out by these events. All right, that's probably enough. So without further ado, our speaker today is Pablo Jarillo-Herrero.
Thank you very much, Alex, for that kind introduction. So I want to start by thanking, the university, Alex, the Fine Institute, and especially the Misel family and the Fine families for the support of the department and for inviting me to be here with you. I have been already in Minnesota a few times, enjoying actually some of the workshops that are organized by the Fine Institute. So I've been a beneficiary also of the generosity of these families. And I hear that the Misel family is online. I made a little bit of effort to integrate the Misel family into my lecture there, as you can see in these pictures. And I also had the pleasure of meeting Bianca Fine during dinner today. So I got at least to meet part of the benefactors, and I'm very happy to be here. So I want to tell you about magic angle graphene, which I'm calling the twist and shout of quantum materials, and you will immediately see why this is the case. Yeah? But I know that this is a broad audience, okay? And I want to start by asking the audience, so, what do you think that determines the properties of materials? Any guesses among the audience? Why does a material behave the way they behave? Electronic properties, for example. Yeah, electronic properties. No, those are properties, but why? What determines those electronic properties? Atomic structure. Very good. That was my guess too, you see? So first guess could be the chemical composition, it's more or less, relates to atoms, so the chemical composition, right? So for example, we have gold, which is a very good metal, not only used in jewelry, but actually in high-performance electronics. We also have aluminum, which is also a good metal, but it turns out if you cool it down, it's a superconductor, okay? Also used in high-performance quantum electronics. For example, if you take iron, we know that it is a magnet, which is also used in many applications. If you take silicon, it is a semiconductor. It's used in chips. So it seems like if you take a given element of the periodic table, it will have certain properties, and that's what determines the properties. That might be a good first guess. However, what about carbon? Okay? Turns out that carbon is the material that is in your pencils. It's graphite, and it's a good electrical conductor. It's made 100% of carbon, graphite. But diamond is also made 100% from carbon. Yeah? Do we have a train passing by? Okay, no? We'll continue. We'll continue. So diamond, which is also made entirely out of carbon atoms, is an electrical insulator. Therefore, it's not only chemical composition that determines the properties of materials. There must be something else. Any guess? What's the difference? Or what's the additional thing? The bonding, the structure, okay? We say that the crystalline lattices, okay, also matter a lot, okay? So the carbon atoms in graphite and in diamond, they're arranged very differently, okay? In particular, in graphite, which is an electrical conductor, the carbon atoms are arranged in sheets, okay? Whereas in diamond, they are arranged in cubes, you know, covalently bonded. Yeah? And that's part of the reason, an important and fundamental reason why, despite being all made of carbon, both graphite and diamond, they behave so differently. Yeah? So both crystalline structure and chemical composition are important aspects that define the properties of materials. Yeah? And for a given material, nature, meaning the laws of physics and thermodynamics, usually determine the most favorable arrangement between those atoms in order to have a material. And there's not too much that you can do about it, yeah? Unless you do something very dramatic, like breaking a material apart or applying a huge pressure. The crystalline structure of a material cannot be changed easily. Yeah? Now, that was until 2D materials came on the market. Yeah? So this is what I want to tell you about today. We're going to start with the twist. Okay, we're going to tell you about 2D materials, and what do I mean by 2D materials? We'll talk about Lego, we'll talk about something called twistronics, and then I'll tell you about specific 2D material, which is very interesting. It's called graphene, and what my group discoveries were involving something called magic angle graphene superlattices. And then I'll come to this shout, what was the actual discoveries that we made, and an outlook of how is the field evolving and how is this thing growing and what is its impact. Yeah? So let me start with 2D materials, Legoland and twistronics. All right, so some of you may be wondering again, this is a broad audience, okay, so what do I mean exactly by 2D? Okay? Imagine you have a deck of cards, okay? It has bulk, it has width, length, and height. It's a bulky thing, okay? However, if you take a single sheet, a single card out of this deck, it has length and width, but it barely has any height, okay? You start to get this idea that this is mostly two-dimensional. Yeah? Now, one thing that some of you may know, but probably some of you do not know, is that if you take a pencil and you write, effectively what you're doing is you're taking a deck of cards and spreading it on a piece of paper. That's what a pencil trace is. Yeah? I'll show you some pictures in a moment. Now, if you take a three-dimensional object like this apple, okay? And this apple is bulk. Let's imagine now that I slice it into sort of two-dimensional pieces of apple, okay? Take an apple slice here. What do you think it's going to smell, taste like? Will it smell like an apple or like something else? I see plenty of faces saying it will smell, it will taste like a chunk of apple, right? Indeed. But what if I would tell you that just by slicing it into a very thin slice of apple, this thing tasted like an orange? That would be pretty amazing, right? Well, that's actually what happens when we take some of these three-dimensional materials and we take them down, we take a slice down to the atomic limit. They completely change their properties. okay? So I want to tell you a little bit about this. But not only that, something even more profound and astonishing that happens when you recombine those slices, okay? So let's go through this journey. So the first material I want to talk about is graphite again, okay? It's the thing that is at the tip of your pencils, okay? And as I said, when you write with a pencil, you're actually spreading layers of graphite. It's like spreading a deck of cards on a piece of paper. Okay? So if you actually go and look at a piece of paper with a powerful microscope and look at what is it that the pencil trace is made of, it's something like this. Okay? You see things which you can already appreciate that this has layers on it. Okay? These layers are not atomically thin, they're a little bit thicker, but you can zoom in a bit more, and then you see more layers, okay? There are plenty of layers, but now you get an appreciation that some of these layers are thinner and thinner and thinner. In fact, if you could look carefully at the very top, you would see that the layer of carbon atoms there, it looks like this. This is graphene, a single atom thick sheet of graphite. Okay? It's something which is one atom in thickness. Just to give you an idea, if you take a hair, okay, from your head, and you slice it along the diameter, okay, so 100,000 times, that's about how thin graphene is. Okay? So it's extremely thin. And for a long time, physicists thought that this thing, graphene, would not exist. It existed in theory, but they didn't think it existed in reality. There is even a mathematical theorem that forbids that graphene exists. Okay? Well, never trust mathematical theorems, They end up not working in the end, High respect for my mathematical friends, but in mathematics, you have many conditions under which your theorem applies. And in real life, often those conditions do not apply. Yeah? So two famous physicists, Undergime and Kostyantov, were very creative. They didn't know about this mathematical theorem, and they decided to try to see if they could get graphene. And you may think that given how thin this is, one atom, 100,000 times smaller than a hair, it must be very hard to get it. Actually, it was surprisingly simple to obtain. All they had to do is to get some Scotch tape, literally, Scotch tape, and some graphite powder. Yeah? So I'm going to show you how you actually can get this one atom thick material. This is my hand, actually, this is a picture of my hand. And there are some graphite crystals in there. And then you take Scotch tape, literally, as you can see, and you put a flake of graphite, a crystal of graphite, in the Scotch tape, and you do like this and split it into two pieces, right? Graphite slices, exfoliates very easily, so you split it into two pieces. Then you can shift a little bit the tape and do this again, and you split it into 4 pieces, 8 pieces. You do this until you get bored, more or less, okay? And your entire tape is covered with thin graphite. And then you take this tape and press it down on a silicon chip, and you remove it, you pull it slowly, okay? Turns out in this tape, together with all that shiny graphite, every now and then, there is an atomic plane of graphite sort of sticking out a little bit. And it gets stuck to the silicon piece. So you end up with something like this. This is, okay, you can see here. Maybe let me use my mouse. Is my mouse appearing here? Yeah. This is one atom thick sheet of graphite that you can see with your eye, actually. It's just with an optical microscope. But this piece is actually large enough that you might be able to see it just with your bare eye. Next to it, you see something a bit thicker. This is 3 layers thick, okay? So you get these graphene crystals. And if you put them in a now super powerful transmission electron microscope, this is what it looks like. This is an actual picture, electronic microscope picture of the atoms, the carbon atoms in a honeycomb structure, showing that graphene indeed exists. Okay? So for the isolation and the study, the early studies of the properties of graphene, Kostyantov and Andrew Geim earned the 2010 Nobel Prize in Physics. People always joke, all you need is Scotch tape and chunk of graphite. That's how you get a Nobel Prize. But people have to think, true, but what it required is creativity and a lot of risk. Not thinking that because mathematical theorem forbids something, you should not try to get it. Now, I'm getting a little bit ahead of myself. So, at the end of my PhD, this is how I looked, So this was in 2005. As Alex mentioned, I was in the Netherlands, in the beautiful town of Delft. I encourage you all to visit. Gorgeous little town, very nice looking, very pretty. And I finished my PhD, and I thought, like, okay, what should I investigate now? I didn't know what to do. And then my PhD advisor, Leo Kanwanhaven, told me, have you heard about this amazing 2D material called graphene? It had just been discovered the year before, and isolated. And I was like, oh, what? No, I didn't know about it. But it seemed really fascinating, so I went to Manchester, where Andrew Geim and Kostin Abosolov were, and they were extremely kind, and they showed me, and a couple of other friends that we went from Delft, how to exfoliate, how to use Scotch tape to isolate and to obtain graphene devices, okay? They were extremely generous with their time, and I benefited a lot from that openness and generosity in the community, which has permeated to this day. This community is actually very open, and I think it started with the founders, being very open and generous. So I went there, and I learned how to, let me actually say, I had to go twice. The first time I thought I got it, went back to the Netherlands, I had to return, That was, hard to ask for a second time, but they were generous to host me a second time, So that was very good. Now, from there I went to New York, and then I ended up at MIT, where I have been doing research in graphene and other two-dimensional materials for a while. So now, what is so special about graphene? Okay, so it's 1 atom thick, but it turns out it has many superlatives. It's the strongest material that exists in the world, stronger than diamond. At the same time, it's very flexible. It's like a sheet. It's hard to stretch a sheet, but it's very flexible. It's the best electrical conductor also in the world, but at the same time, it's transparent. Most metals, copper, gold, they're opaque, but graphene, because it's very thin, is a very good electrical conductor, yet at the same time, it's transparent. It's also the best thermal conductor in the world. It has many, many fascinating properties, okay? In fact, one thing that is very exotic about graphene is that electrons in graphene behave as ultra-relativistic particles, the type of particles that people accelerate at the particle physics accelerators, like this one. This is a picture of CERN, okay? So in some sense, you can think of graphene as this giant particle accelerator, okay? Where you can imagine covering all of CERN with a graphene sheet and studying the behavior of those particles. Now, this is not something that we're used to in material science, electrons behaving that way. So let me tell you a little bit, just so that you catch how different the behavior of electrons in graphene is from electrons in other materials. Let's do an experiment. We're going to start with classical physics before we go to quantum physics. So let's start with classical physics. Therefore, we're going to bring Isaac Newton, okay? And we're going to put a wall in front of Isaac Newton, okay? And we're going to ask Isaac Newton to throw tennis balls, classical tennis balls, to this wall. What happens if Newton throws tennis balls at the wall? What do you expect? Comes back. Indeed, okay? Newton is there, and the tennis ball just comes back. That's what classical physics tells you it should happen. Let's move on to the quantum world. Let's take Erwin Schrödinger from the famous Schrödinger equation. Let's give him, let's put a quantum wall in front of him, and let's give him quantum tennis balls, okay? So if Schrödinger now throws tennis balls at the wall, most of the time, those tennis balls bounce back, okay? Like in classical physics. But every now and then, a ball makes it through the wall. That's a process called quantum tunneling. It's very unusual. People were very puzzled by it, at the beginning of the 20th century. It turns out, maybe you don't know about this, but absolutely all, 100% of the technology that you use is based on this effect, okay? Because we wouldn't understand semiconductors, chips, and all those things without understanding tunneling. So 100% of the technology, modern technology, works based on that effect. It's very unusual, okay? But yeah, we know that it works that way. That's how silicon works. That's how 99.9% of the materials work. Now let's take ultra-relativistic physics. Who is the relativity scientist? Einstein, indeed. So let's take Einstein, and let's put a wall in front of Einstein, and let's give him ultra-relativistic tennis balls, okay? And now let's ask Einstein to throw those ultra-relativistic tennis balls at the wall. Guess what? They make it through always, 100% of the time, okay? Always. This thing is a phenomenon that is known as Klein tunneling. It was proposed theoretically in 1929, and forgotten because you could never do this, forgotten for nearly 80 years, until graphene came on the market. People look at the electronic properties of electrons in graphene, they realize they behave like ultra-relativistic tennis balls, and they could measure that, indeed, that's the case. And that's the reason why graphene is the best conductor, because electrons in graphene go through obstacles. Usually obstacles bounce electrons back and prevent them from moving. In graphene, choop, 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 you go through all the obstacles, and that's why it's the best conductor in the world, okay, largely. So graphene is amazing, but it turns out that it's not the only two-dimensional material. We have plenty of two-dimensional materials. And one of them is hexagonal boron nitride. It's also a honeycomb. It's the thinnest insulator in the world. It's not a conductor, it's an insulator. It's the thinnest insulator. You also have semiconductors like tungsten diselenide, yeah, which also looks like a honeycomb. Yeah, honeycomb is a frequent motif in these two-dimensional materials. Turns out the electronic properties of tungsten diselenide change quite dramatically with layer number. If you get one layer, it's a visible light emitter. If you get two layers, it's an infrared emitter. Yeah? And these semiconductors can be very useful for technologies. For example, a few years ago, almost, by now 10 years ago, my group showed that you can make the world's thinnest light-emitting diode, LED, okay, less than a nanometer in thickness using this tungsten diselenide. Okay? So these 2D materials have many different properties, and they're very interesting, both for fundamental science as well as for applications. But not only we have many 2D materials extracted out of those decks of cards, but we can reassemble them into a new deck, okay, by choosing pieces from different decks, okay? I could choose this particular combination, or I could choose an entirely different one. And the properties of the combined heterostructure differ depending on which combination I make, yeah? This is something which, stacking to the layers is the new 3D. And I was talking once to a great chef, famous chef, Ferran Adrià, one of the world's greatest chefs, which was visiting the lab. He was like, I don't get it. I was trying to explain this to him. And he said, like, oh, this is like a mil hojas, which is like a millefeuille in Spanish. And indeed, this is a process similar to that, where what you put together usually is better than the individual pieces, So now, this led, to the term 2D materials Legoland, the fact that you can put things together on top of each other. However, the world of 2D materials is even more exotic than that, okay? Because, I have small kids, I'm sure plenty of you too, and or grandsons, granddaughters. And when you play with Lego, you have to stack all of the layers on top of each other, aligned at the right angle. Otherwise, sometimes my kid comes like, Daddy, I cannot stack this layer on top of the other. And I'm like, that's because you have to rotate it to 0 degrees, okay, or 90 degrees. But the most unique aspect of these van der Waals materials is not this Legoland aspect, which is quite unique already, but it's the following thing, okay? And here's where the twist comes. I can take a two-dimensional material, for example, a piece of graphene with these hexagons that you see on the screen, and I can place another 2D material on top, another card on top, like this, like in Lego, but I can also do it with any rotation angle between the two layers that I want, okay? I can choose 30 degrees, 27 degrees, 1.1 degrees, as I will show later. Why not? This creates the superposition of two periodic structures rotated one with respect to the other creates something known as a moiré pattern. And I have here two toys that I'm going to pass around the audience. You know, these are two layers of graphene simulating, and you can rotate them, and you can see the effect of this moiré pattern. So I'm going to pass one here. I hope to get them back. So, and let me stop this so that you don't get too dizzy. So, this moiré pattern, you know, the ability to change the crystalline angle between materials, that's something that is unprecedented in the history of material science. We could never do that. Nature tells us what the angle between planes, atomic planes, is in materials. But because now we have these two-dimensional materials, we can tune this, we can play with this. And what I'm going to tell you is that when you put two things together with a twist angle, the properties change dramatically, much more than going from apple to orange, in fact, okay? Much more in the equivalent physics sense. Yeah? So let me tell you a bit more about graphene and magic angle graphene. So again, when you rotate two structures on top of each other, you know, you generate this super periodic pattern called a moiré structure, where the distance between the soccer balls that you see here in the screen is called the moiré wavelength, okay? And it can go all the way to infinity for small angles. Now, let me compare graphene versus magic angle twisted bilayer graphene. This is going to be a baby introduction to the subject. If you want to hear a bit more professional introduction to the subject, come tomorrow to the colloquium. I'll try to present it today in very simple terms. So you take graphene, and you look how the electrons move through graphene. Okay? You can plot something which is known as the kinetic energy of the electron, the energy related to motion, versus momentum, which has to do with you know, in which direction you move and how fast you go in classical physics. Now, for electrons in graphene, that relationship is straight lines. It's a cone because it's in 2 dimensions. So here I'm projecting in 1D, it's a straight line. Okay? Now, all I want you to get out of these straight lines is that it's very steep. And steep slope means very fast electrons. Okay? And not only that, it's a constant slope. And the slope tells you what is the velocity of the electrons. Yeah? It is because of this linear slope, the electrons always go at the same speed regardless of their energy, that electrons in graphene behave like these ultra-relativistic particles. And the speed of light is constant independently of whether you're talking about infrared light, X-rays, visible light. The speed of the electrons in graphene is also constant independent of their energy. Now, if you take magic angle twisted bilayer graphene, which means you take 2 sheets of graphene and you place them on top of each other, rotated with a precise angle of 1.1 degree. 0.9 doesn't work, and 1.3 doesn't work, okay? 1.1 plus minus 0.1, give or take. Yeah? Then what happens is that the kinetic energy of the electrons versus momentum looks like this. Looks very flat, okay? It has a very small slope, which means your electrons propagate very slowly through this structure. Okay? And this we get just by rotating that 1 degree. Okay? We say that this is a flat band for those which are a bit experts in the audience. Now, why is this important, whether the electrons go fast or go slow? Well, if the electrons go very fast, the Coulomb repulsion between the electrons, because they're charged particles of the same sign, they repel each other, is barely noticeable. They go shoom, past each other very fast. They don't have time to notice that they're repelling each other, okay? However, when electrons go very slow, they have a lot of time to notice that they have the same sign charge and they repel each other. I always make an analogy which is not very scientific, so colleagues, please forgive me, but I think it may help for the broad audience. This is like if you walk on the street of a big city, okay, like New York, and you're walking very fast past each other. You barely have time to talk, to interact with the other person. Interactions don't play a major role in a big city. But if you live in a small town where everybody walks a little bit more slowly, you have a lot of time to stop and talk to each other and interact, before you go, you go back to your business, okay? Not a perfect analogy, but I think it helps a little bit, okay? So interactions are very important when the electrons go very slow, not so much when the electrons go very fast. Okay? And in magic angle graphene, the electrons go very slow. Now, why do I say all this concept of interactions? Why did I bring it in? Well, when you look at quantum matter, quantum materials, and materials or matter in general, where quantum physics plays a very important role, there are two types of behaviors that one can look at. One is, we call it a single particle behavior. For example, take a single electron, represented here by this particle with an arrow, which represents a spin. Take a single particle with a spin. The behavior of a single particle is simple. And by that, I mean we understand it mathematically, we understand it theoretically very well. However, if we have many particles interacting with each other, that behavior, that many particle behavior, is actually very difficult. Okay? It is not understood. Despite a century of physicists working on the behavior of many particles, we do not understand it yet. We don't have the proper mathematics. We do not have proper computers to solve these problems numerically for more than a handful of particles, certainly not for 1 billion of electrons in a material. Yeah? So because we do not know this is very annoying. And you may think like, well, who cares? Maybe it doesn't matter. But actually it matters because the majority of the most fascinating states of matter and behaviors that we have in the universe are due to strongly interacting particles, which means we do not understand the majority of the fascinating behavior that occurs in the universe. And whether this happens everywhere, this happens in the quark gluon plasma, which occurs a few seconds after the Big Bang, and that we can recreate now in particle accelerators. It happens also in neutron stars, which happen after supernovae explosions, where you have lots of neutrons interacting very strongly. It happens also in the world of quantum materials, for example, high-temperature superconductors, which are very important for many applications. We have no idea how they work, okay? So traditionally, we have done the following. Okay? For many years, 100 years plus, we have been looking at the behavior of quantum materials by looking at different actual materials. I have this material that I grow. Now I look at a different material. I try to experimentally see what I can understand from its properties. I have very little tunability over these materials because for each one I have to do, build a different chemical composition, a different structure, etc. The cold atom physicists figured out something in the past 20 years which was quite interesting. They thought, oh, I can shine lasers at each other. I can create a periodic potential where I can load atoms, and I can tune the interactions. So I can build quantum simulators, are called, of materials, on these optical lattices. Yeah? And the good thing is that they have exquisite control over all the parameters of the system. They have much more tunability than we have with traditional quantum materials. So these two platforms have been the two traditional platforms to investigate strongly interacting, strongly correlated, and topological physics, new materials, and new behaviors of matter. And what I want to tell you in the rest of my talk today is that a new platform has emerged in the past 6 years called the moiré quantum matter platform. It is very nicely complementary in length scales and in many aspects to these other two platforms. For materials, you have an angstrom, length scale. For cold atoms, is the wavelength of light, a micron. That is the appropriate length scale. For this moiré quantum matter, the moiré wavelength is typically of order 10 nanometers. So a factor 100 from these other platforms. And the nice thing is that we have quite a bit of tunability, not as much as with the cold atoms, but much more than in traditional quantum materials. But we have been able to see many more things in a very short period of time than the cold atoms community has been able to reach so far, because the long distances in the cold atoms community means they have a hard time cooling down in temperature to see some of the exotic quantum behavior that we'd like to see. It is very, very hard to do that. Yeah? So for the experts, just one slide intermezzo, the Dirac cones of graphene, okay, from the electrons in layer graphene 1 and layer graphene 2, when they get close together, they lead to a band repulsion, which pushes one band to 0 energy, and you reach a flat band condition, and that flat band condition is at the magic angle, and it's 1.1 degrees for graphene on top of graphene due to the tunneling of the electrons between the layers, okay? This was theoretically predicted, that the electrons would go very slow, but that was a single particle physics prediction. Nobody knew what would happen when you put many of those slow electrons in graphene. Those flat bands, okay, this is, you can see here, this is the blue band is the flat bands. Red ones are other bands which are higher in energy that we don't care about for now. But in a flat object in momentum space, remember this label, momentum space, if you want to go to real space, you have to do something called a Fourier transform, a mathematical Fourier transform. And the Fourier transform of a very extended object is a highly peaked object, which means that electrons in graphene, when you put electrons in magic angle twisted bilayer graphene, they like to sit in certain regions of your moiré pattern. You can see this distribution is highly peaked in certain regions and not in others. Okay? So from the top, magic angle graphene looks like this. It looks like these regions of their so-called AA stacking, where locally the carbon atoms are on top of each other. But because of the small twist angle, the atoms get out of registry, and these regions of AB and BA stacking, the electrons do not like to be there. In a slightly more realistic schematic, this is what magic angle twisted bilayer graphene looks like. You have these A8 regions shaded here in yellow, where the electrons like to be. Now you can see that this looks a little bit like those ultra-cold atoms simulators, but I'm placing electrons in there rather than big atoms, and I'm doing that on a 10, 13 nanometer length scale. Okay, so what happened then? Yeah? Let me first tell you how we actually build these structures. How do we do this then? It's very simple, not quite as simple as Scotch tape and crystals of graphite, but it's actually quite simple, much simpler than you may think. So we start with a glass slide, which has a sticky polymer attached to it. And then we bring a substrate which has a thick layer of hexagonal boron nitride, 10 nanometers. I mean, still thin, but not atomically thin. This is going to be just an ultra-flat substrate, very comfortable for the graphene to be attached to. So I come with my sticky polymer, and I pick it up. I pick this HBN crystal. Then I bring another substrate where I have graphene on it. As I showed you before, we do this with Scotch tape. Still to this day, we do it with Scotch tape, okay? And what I can do is I can position my hexagonal boron nitride flake sort of on top and in the middle of the graphene sheet. So that now I come down and I tear half of the graphene, okay? So from the top, this looks like I have my silicon substrate with half of the graphene, and I have my glass slide with my polymer, with my HBN, and the other half of the graphene on it. But even though these are at different heights, two pieces of graphene come from the same crystal. So the atomic rows here are aligned with the atomic rows here. I know exactly what's the orientation of this with respect to this. So what I can do now is I can rotate my substrate, and I can, by any angle that I want, for example, 1.1 degree, why not? And then I can translate this polymer with this light, and the top graphene layer, and stack it on top. And I pick up the second layer of graphene. And amazingly, I'm able to form this very regular moiré pattern, and continue doing processing to make a microelectronic device with this. Yeah? This thing is very simple. A high schooler that comes to my lab learns it in a couple afternoons, okay? But it takes quite a bit of dexterity. If you try to do it on your own without having practice for a year, without having teaching you, it's not so easy, yeah? Because you have to think that in reality, this is more like if you take plastic wrap, put it on your kitchen table, one layer, without a single wrinkle, and then you tear half of the plastic wrap without a single wrinkle, and put the other one 1.1 degree on top without a single wrinkle, okay? So it's like that, okay? So it requires, perseverance, and my students have golden hands, so, that's great. All right, so then we continue doing nanofabrication of this, and we come up with a device which looks like this. It has our twisted bilayer graphene at the magic angle or at any angle that we choose. It has top and bottom hexagonal boron nitride, so that it makes a nice sandwich protected there, protecting the graphene. And we contact the graphene with source and drain electrodes, so that we can apply a voltage and measure a current circulating through it. And we do all this in a field effect transistor geometry, for those of you who are engineers, or basically, we have an extra additional metallic plate. The graphene and this metallic plate form a parallel plate capacitor. So if I apply a voltage, I can change the density of carriers in the twisted bilayer graphene, okay? So then, the shout, what we discovered when we measured these devices, was that, and this is going to be a bit technical, but I just want you to get away with a message, Basically, graphene, which is the best conductor in the world, you put it on top of graphene, which is the best conductor in the world, and when you put it together, it becomes an insulator. And not a regular insulator like diamond, but a correlated insulator. An insulator where it is the interactions between the electrons that prevent them from moving, okay? That was surprise number one. And here, this G means conductance, conductivity, and this 0 is meant to show that it doesn't conduct, okay? Now, that occurs for a specific number of electrons in this moiré pattern. It doesn't happen everywhere. It happens when we put 2 electrons, or when we remove 2 electrons from this moiré pattern, okay? And then the even bigger surprise is that if we now add a few extra electrons to the entire structure, it goes from being an insulator to be a superconductor, okay? And that was a huge surprise, because although graphene is the best conductor in the world, it's not a superconductor. It's the best ordinary conductor in the world. But we put 2 of these things together at that angle, and it became, depending on how we dial our voltage knob, an insulator where the electrons are locked and cannot move, or a high-speed highway for electrons, where they superconduct without dissipation of energy, okay? And all of this happens only 1.1 plus minus 0.1 degrees of rotation between the sheets, okay? It's a very, tuned behavior, magical almost, I think the term magic angle graphene was invented before they saw this thing, but it is even more magical now that we saw this thing. So it is also very special because this superconductivity, which is electrically tunable, superconductors usually are not electrically tunable, but here I can tune it. Do I want a superconductor or not? Depending with this voltage knob, how many electrons I put in it, happens next to this insulating behavior. And the entire physics community knows that that behavior is very reminiscent of the behavior of high-temperature cuprate superconductors, where the superconducting behavior happens next to a correlated insulator behavior, okay? So when my students showed me this data, I was immediately shocked, because this reminded me of the hundreds of times that I had seen these diagrams. Let me flip it, because now electrons and holes are in the right direction. Okay? In high-temperature cuprate superconductors, when you put 1 electron per copper atom, you get a correlated mode insulator. And if you add a few extra electrons or a few extra holes, you get superconductivity. In magic angle twisted bilayer graphene, when you put 2 electrons or 2 holes per moiré unit cell, you get a correlated insulator, and you add some holes or electrons, and you get a superconductor. Okay? Now, there's a big difference between these 2 diagrams. This thing is a theoretical phase diagram. Meaning, in order to populate this plot with actual experimental data points, you have to grow hundreds of crystals, each with a different chemical composition, because not all materials grow, for electrons and for holes and for different compositions of electrons and holes. Whereas this plot that is here is a real experimental plot. In one device, I just dial a knob, and I can go from here to here and build this plot in a few seconds, okay? In a single disordered realization without having to grow multiple samples or devices. So that obviously is something that is advantageous to study the properties of these materials. Now, I should mention that although there are many similarities between these systems, there are also many, many differences, okay? So the analogy only takes you so far. Okay, so we posted this at the APS March meeting in 2018. And then what I call the theory tsunami came, which is that this is a list of the papers that were published in the first 2 weeks after we posted our experimental results. By now, that list has several thousand papers, okay? Everybody wanted to know what, is this superconductivity? What is this correlated insulator? Why is this material doing these things, okay? I always joke with people that in the field of single particle physics, like, when you do vanilla graphene, just one layer, the disagreement between the theories, the angle of disagreement between the theories is about 20 degrees, more or less. They have some differences, but they mostly agree. In this field of many particle physics, interacting physics, the angle of disagreement is 360 degrees, In fact, it's 4 pi, it's in all directions, So theories do not agree at all with each other. There are many fights. Which assumption did you take? Which approximation did you make? I don't agree with you. For me, sociologically, it has been very, interesting to experience this, So, this also attracted attention from the popular press and different journals to make super cool graphics about what is going on, with these sheets, and this, I wish I knew how to make these graphics. Anyway, so but perhaps more importantly, and with this I'm going to go towards the end of the talk, what happened theoretically is what has happened experimentally since our discovery, okay? So the first thing, which is very important, especially for important lesson for the young people here, is we have reproduced our own results, Believe it or not, that doesn't always happen. It's very good when you're able to reproduce your own results, okay? Now, even better than you reproducing your own results is when someone else completely independently reproduces your results. Only then it becomes real science, okay? And luckily for us, our products have been reproduced by many, many groups now all over the world and have been extended to many other interesting systems. So we have discovered plenty of other phenomenology, which is characteristics of these very strongly interacting quantum materials, such as strange metal behavior, pneumaticity, Fermi-Cepheid reconstructions, things that maybe don't mean too much to some of you, but for the quantum materials community, it's very important to see those behaviors because they're not understood. We have also discovered many other correlated systems. It's not just graphene twisted on top of graphene, but you have ABC graphene on top of HBN, magic angle twisted bilayer graphene. We call it, twisted by. When you put 2 layers on top of 2 layers twisted, so 4 layers in total. We have the transition metal dichalcogenide, those semiconductors that I mentioned that emit light. You can twist them also on top of each other, and the properties change dramatically. Okay? We have many, many systems now which are strongly correlated. The community also discovered ferromagnetism, anomalous Hall, and integer and fractional quantum anomalous Hall physics in these systems. Yeah? Now, what that means is that there is this branch of mathematics called topology, which plays a super important role in the behavior of these materials. Yeah? In fact, something which has been very satisfying for me is that this moiré quantum matter field has brought together several fields of physics that didn't used to talk too much to each other. The people that did graphene and 2D materials, like myself, together with the people that did strongly correlated materials, like high-temperature superconductors, pnictides, heavy fermions, and the people that do topological condensed matter physics, quantum Hall effect, topological insulators, etc. All 3 communities come together because the physics of all these 3 communities is very important for moiré quantum structures, and that's something which is I enjoy very much talking to so many people that I didn't used to interact with. This is surface. It's ultra thin, so you can do many local probe studies and investigate with scanning tiny microscopy, scanning nanosquid, scanning ACT, scanning near optical field microscopy, scanning transmission electron microscopy, and the community has invented even new techniques. There's something called the quantum twisting microscope to study these materials, because nowadays, not only we can make the structure with any angle that we want, we can in situ change the angle and study the properties as we change the angle, okay? So that's fantastic, and it's a very new development. The other thing is, why stop at 2 layers? We can do 3, more magic, 3.0, I call it, and 4.0 and 5.0, okay? So a few years ago, my group and the group of Philip Kim, my postdoc advisor in New York, we published back-to-back papers in Nature and Science showing that if you do 3 layers at a magic angle, which is not 1.1, is 1.57, you get an even stronger and more interesting superconductor. Okay? Plenty of things have happened in this field. Let me tell you a bit more. So using these 3 platforms now, we have a much better grasp of what's going on with strongly interacting matter. And as I mentioned, this traditionally has shown us many behaviors, but we have little control. This one, exquisite control, but so far, we don't have as many behaviors as we would like. They have not been observed. But with this one, with moiré quantum matter, in the span of a few years now, we have observed all of the behaviors of matter known, and in fact discover quite a few new ones that weren't known, okay? So we have been able, just by twisting, okay, and basically with graphene, maybe with 1 or 2 other materials, we have been able to realize exotic correlated insulators, unconventional superconductors, new topological phases which were not known before, magnets, quasi-crystals, ferroelectrics, strange metals, generalized magnetic crystals, excitonic insulators, you name it, tell me a behavior of matter, it has been seen using these moiré quantum matter structures. Yeah? But not only that, this is all in the field of twist electronics, which is how this all started. But then people started to realize that we could apply the exact same tricks to many other things. For example, our friends, the cold atom physicists, started to do moiré and twisted cold atoms lattices. Started with theoretical papers, but now in China, they have created already the first twisted optical lattices to study ultra-cold atoms in optical lattices rotated to simulate these new twisted materials. The trick that you do with electrons and with the speed of the electrons, you can also do it with phonons or with the vibrations of materials to slow down the speed of sound. So there are this field called now moiré and twisted phononics, where either at the microscopic level of atoms or at the macroscopic level of literally plates vibrating, you can rotate them such that you slow the speed of sound, and it cannot propagate through material, okay? Or it propagates very slowly. Yeah? If you can do it with sound, why not do it with light? And indeed, this field of moiré and twisted photonics, which is the fastest growing field after the electronics, has shown that you can also slow down the speed of light when you twist your photonic lattices, okay? And, light goes very fast, right? So if you slow it down a lot, you can realize all kind of nonlinear optical phenomena. And the Department of Defense has now entire programs, about this topic, because of the possibilities for applications. Why stop there? The chemists realize that these moiré systems, where the electrons like to sit in certain places, where the electrons are, the chemical reactions will take place. So there is this field of moiré and twisted electrochemistry and catalysis, where these twisted structures have been seen now that they exhibit local chemical reactivity that depends on where you are, and in some cases, they can produce much better catalysts than existing catalysts for a variety of chemical reactions. Yeah? And last but not least, our high-energy physics friends, the ones at CERN, thought that they couldn't be any less, so that this field also called moiré gravity and cosmology, where people think that by twisting graphene sheets, you may gain some insight into the properties of space and time, okay? So with this, I want to end with what is actually the most important slide, which is the acknowledgements. This is not something that I do myself. It's something which is done with a large group of people, a fantastic group of students and postdocs and collaborators. I also have to acknowledge the funding and support from various funding agencies, industry, and also foundations. And I'm very glad that after a few years, now we can get back to this type of meetings, all in person together. This is a paella dinner, traditional from Valencia. made by myself, okay? I want to thank you all for your attention. And I'm happy to take questions.
Can you comment on the durability of these materials, especially if you're doping to adjust the electron properties, if you get any migration and changes in the properties?
Very good question. Infinity. They endure forever. These materials, because they're van der Waals materials, they have relatively little chemical reactivity. And because the electrons we're introducing them electrostatically, dialing a voltage knob, not by introducing impurities, chemical impurities, and removing them, and so on, you can oscillate. I will mention, tomorrow during my colloquium, but we have made, one of the things that we have made twisting these materials is a ferroelectric material. In a ferroelectric material, you switch a dipole moment up and down. It is very good for memory, for example, applications. But industry is struggling because when you switch it up, down, a regular material, after a few thousands or hundreds of thousands or millions of cycles, they degrade. Ours, we can do 100 billion times, and we just got bored, we stopped. It was on, off, forever. So the durability of these materials is very, very high, okay? Especially in the case of graphene, which is, and hexagonal boronitride, which are relatively inert. Some other 2D materials, you have to be a little bit careful, and you have to encapsulate them properly. Okay.
So, when you're working with your group, and presumably this picture of your correlated insulator and superconductivity, it all come at once. So, you got the correlated.
Maybe use the microphone so that the Misel family who is on Zoom can listen to the talk.
So, so presumably you saw the correlated insulator first, and at that point you were happy, right? And then did you tell your grad student, add a few more electrons and see what happens? Or what was the process?
That was indeed an interesting story. So, let me see where here it is. So my students, they showed me, they showed me first, well, after many, many, many measurements, we got this plot, right? And we saw that there was this conductivity 0, conductivity 0. It was very strange that it was 0. We knew it was not supposed to be 0. So it was very strange. And then my student tells me, you see, there is a peak next to it. There is like this peak in conductivity. It seems like this thing wants to conduct well. And we joked, can you imagine that this was a superconductor when you just add a few electrons? But we totally didn't think this could be possibly the case, And then my student looks at me and says, because these devices, they were 2-terminal devices, which means a graphene, source, and drain electrode. I was looking for insulators, but not of the type that we found, okay? But there were some reasons to look at insulating behavior. And when you're looking for an insulator, since the object that you're looking at is an insulator, you don't care if there's a little bit of additional resistance from the contacts to that object. And that's why we had what is known as 2-terminal conductivity measurements and devices. If you want to see something superconduct, that means it has 0 resistance, you cannot have any additional resistance from extra contacts or whatever. So you have to make devices in a geometry which is known as 4-terminal geometry, where you can measure the intrinsic resistance of the object. So my student looks at me and says, do you think we should make 4-terminal devices? In case this is a superconductor? And I look at him and I told him, what are you talking about? Of course we have to check. The chance is 1 in a million, but that peak next to an insulator, let's check. And then, they showed me that the resistance goes to 0 when you go to low temperature, and this thing becomes a superconductor. We couldn't believe it, In fact, I know someone that when I presented this thing at the March meeting of the American Physical Society, 20 years earlier, there was a case of famous scientists at Bell Labs that had shown many amazing things, kind of similar to this. His name was Hendrik Schon. Turns out it was all fake. He had faked all the data. So this person looks at me and says, you know that nothing like this has happened since Hendrik Schon, you know. Like, okay, what do you mean? He says, are you sure you're a Chinese student? Did you look at the data, you know? Yeah, I was pretty sure my student had taken the data properly and not faked it, and you know, I paid close attention, you know. But people were in complete disbelief that this could happen, you know. It was a complete surprise, not predicted, never imagined, yeah.
Well, when you believed it, did you twist and shout? Did you
Oh,
like, what was?
I cried. I don't know if you noticed, but still I cry, you know, 6 years later when I remember, you know. It was, you know, a spectacular feeling, yeah. Yeah.
I had a question about the hexagonal boron nitride specifically. Had anyone in your group or any of the other people who've started working in this tried twisting the boron nitride layers with respect to each other and see if you quit getting just the insulator effect and it becomes conductive at the right angle?
Very good. So hexagonal boron nitride, an individual layer, is an insulator. And it's a very strong insulator, a huge band gap, okay? So by twisting it, it doesn't become a conductor. But by twisting it, sorry, it becomes a ferroelectric material, for example, okay? Which a single layer is not, and bulk boron nitride is not. So it also can change dramatically its behavior, okay? These 100 billion cycles that I mentioned a moment ago about, you know, ferroelectricity is in twisted hexagonal boron nitride, actually. So it's a very interesting material also, but it does not become so far a conductor. It's too strong an insulator. Yeah.
Hi, I had a question.
Yep.
So, have you tried intersecting graphene sheets instead of stacking them and then analyzing the electronic property at the intersection?
Sorry, can you repeat?
Like, have you tried intersecting the graphene sheets instead of stacking them?
Putting them in what?
Intersecting.
Oh,
Like,
intersected like
Yeah,
this?
yeah, right.
Oh,
And then,
that's an interesting geometry. You would have to literally cut,
yeah, like,
right? A slit on one graphene sheet to intersect another one like this, okay? So no one has done that, to the best of my knowledge, okay? I'm not sure, because by cutting it, you create a major disruption, you know, to the electrons in the graphene sheet. So right now, I don't know what behavior you may expect from that, but something similar would be to bend it at the right angle, okay? No one has done that, but people have bent it a little bit. And it's interesting because when the electrons have to go through curved space, their behavior can also change. Okay? For example, if you apply a magnetic field, and you have a sheet which is doing like this, and you apply a magnetic field in this direction, the magnetic field is entering the graphene sheet on this side, but it's exiting the graphene sheet on this side because it's bent, okay? And therefore, there are some quantum properties of the electrons which they rotate in a magnetic field, so they would be sort of counter-rotating in these two regions, and that can create interesting effects. Yeah? But that's the closest I can think of.
I'd like to hear a little more about one of the last statements you made in your talk about how you can affect space and time. I think you were talking about the speed of the propagation of light. I'm wondering if we're talking about something as far out as warp drives from this.
Sorry, something that is what?
Warp drives from like Star Trek.
Okay. You know, this always work, you know, when I say that people are working on moiré gravity and cosmology, what it usually means, you know, similar to when I describe the behavior, this ultra-relativistic behavior of electrons in graphene. What it means is you write down the equations, the mathematics for moiré graphene, sometimes under deformation. You write down the equations, and you realize that those equations look formally, qualitatively, very similar to the equations of gravity, cosmology, some particular phenomenon that you're trying to look at or investigate. And therefore, by solving this behavior here, you can learn something about what, or gain some insight about what might be happening there, even though the properties are extremely different. In one case, we're talking about black holes and ultramassive objects. Here we're talking about electrons going through this twisted, tiny structure, okay? But the mathematics can be similar, or they can map one onto another, and therefore you can gain insight from one field onto the other, and vice versa, okay? So, applications to Star Trek? None so far, but I encourage you to look into it.
So I had a question.
I hear a voice, but I don't see.
I'm here.
Oh, here, very good.
So I have two questions. They're very unrelated to each other, but my first question is, so you talked about how theoretically it was actually predicted that you can't extract one single layer of graphene, but you were actually able to do it in a very simplistic manner. So I want to ask, like, why was that the case? Because I feel it's very counterintuitive. Like, if theory says that it's not allowed, like, how is it so simple that you're able to do that? So.
Very good. So let me tell you what that mathematical theorem says. Okay? Mathematical theorem says you cannot have a crystal, an ordered array, periodic array of atoms, in 2 dimensions. Okay? Now, what the mathematician is thinking is 2 dimensions, infinite space. And indeed, no one has managed to make an infinitely large size of the universe graphene sheet. But graphene is the strongest material that exists in the world, which means that when you cut it into a piece, and the piece can be this size, okay? Graphene exists at least up to this size, you know, semiconductor fab wafer scale. You know, the material, which is of finite length now, okay, finite dimensions, actually exists. So the mathematicians, can say, well, I didn't say finite, size, I said infinite, because indeed, if it was infinite, physics tells you that there would be quantum fluctuations of the system such that this material effectively, there would be no correlations between the positions here and here, which means it's not a solid, it's not a crystal or the crystal that exists. Okay? But in practice, by making it finite size where finite can be pretty large, in practice, in reality, once you put the numbers, this thing works pretty well, no problem.
Sorry to take up another question, but I was also kind of curious about ultra-relativistic behavior. At least from my introductory quantum mechanics course, we learned that, if the energy is higher than the potential, it acts like a sine wave or a sinusoidal wave. And as it enters into an area with higher energy, it becomes like an exponential curve. So how does that like sinusoidal, I'm assuming it's like the sinusoidal wave function is maintained. So how is that possible? I'm just kind of curious about that.
Okay, so let me go to, I can go here, for example. All right, so this is one of those backup slides, which is a bit more technical, but, so this is graphene, okay? And you can calculate using quantum mechanics what are the electronic properties of graphene, this kinetic energy versus momentum. And I'm gonna zoom in near where the electrons are, and you can see this is a cone. We call it a Dirac cone. This is very unusual. Usually, the kinetic energy of an object goes as p squared over 2m, or 1/2 mv squared. The more velocity you have, the more kinetic energy you have. But we know from example, for example, from light, that light, it doesn't matter how much energy the photons have. They all go at the speed of light. Radio wave photons, which have very little energy, infrared photons, visible photons, ultraviolet photons, X-rays, and gamma rays. There are 10 orders of magnitude in energy difference between these. They all go at the speed of light, same speed. That is characterized by a linear kinetic energy to momentum relation. And electrons in graphene, unlike 99.99% of materials, because of the symmetry properties of the graphene lattice, have this linear energy momentum relation, as you can see here. And in fact, the equation that governs the behavior of electrons in graphene at those low energies for which you have this linear energy momentum dispersion is here. This is the Dirac equation in 2 dimensions for massless particles, which means it is the equation that governs the behavior of ultra-relativistic. Ultra-relativistic means no mass, zero mass particles, okay? And it's this equation here. So the electrons in graphene do not go at the speed of light. They go at a speed which is actually about 300 times less. It's called the Fermi velocity. But it's constant, independent of their energy. And in that sense, they behave like ultra-relativistic particles.
Hello. I had a quick question about the superglue that you use, the hexagonal boron nitride. The claim is that you use that glue to tear a monolayer graphene and then stack the other on top of it at a 1.1 degree angle. But before that, you also claimed that graphene is infinitely durable. So how does something with infinite durability just get teared off by a superglue?
Very good question. So maybe I exaggerated a little bit when I said infinitely durable. You know, in the end, graphene, and the question by the lady that asked the question is about, how durable is it? And I interpret it in terms of electronic properties. You change it, you do this, you do that when you add charge, which I think was the motivation of the question. And in that sense, it's very robust. Graphene is the strongest material in the world when you normalize by size, okay? But still, an individual sheet of graphene, you can tear it apart with not too much strength. For example, by making use of the van der Waals interaction, which is relatively weak, but when you take it over a large area, can be a substantial force, and you can tear apart these two pieces of graphene with no problem, okay? The strength of my students doing this on an objective, that taking that glass slide up, is much stronger than an individual sheet of graphene, okay? So it's no problem at all, actually.
So you have said that how physics kind of rhymes, like how sound, like sound or light. So in the application of when you're like twisting space, is it possible that time varies among the space-time, varies as you twist the structure?
Very interesting. I don't think you can speak of, in this context, twisting time, or time would vary, okay, as you twist these structures. You're modifying, the properties in real space, and also in momentum space, and also in, terms of the electronic structure, so in energy. But to vary time, that's a concept which is a very weird thing. I'm not sure exactly where your question comes from, but time, from the point of view of these things that I'm talking about, is just parameter that is, ticking. It's a clock that is ticking. We're not modifying time when we do this. In this last slide, when I talk about moiré gravity and cosmology, okay? There in cosmology, space and time, they get sort of intertwined with each other when you go to the things like black holes and so on. You have to watch out when you go to the field of general relativity, okay? I'm not sure if the insights that are trying to obtain in cosmology by twisting graphene sheets, the time aspect, is an important aspect, or it's mostly space deformation, as can be seen in this picture. They're, pretending to be, an analogy of a black hole by deforming, space, maybe time too, but I don't know enough about that.
Yes, hello. Thank you for coming. I'm just wondering if you know any sort of reason why these two-dimensional stacks don't form in nature, particularly? Or if they do, where it could be found, potentially.
The stacks themselves form in nature, okay? Graphite is a crystal that you get in mines, okay? So the stacks themselves form in nature. Isolated 2D sheets, those you do not find in nature regularly, okay? There's some other interesting structures, one-dimensional and zero-dimensional, for example, carbon nanotubes or fullerenes, which are like graphene sheets wrapped into cylinders or wrapped into soccer balls. Those can actually be found in nature, in some circumstances. In space, that's how fullerenes were first discovered. And I know that in some of the best Assyrian, 3,000-year-old swords, they have found carbon nanotubes. Apparently, in the process of making, the swords, they generated carbon nanotubes. I wouldn't say they're in nature; they were still human-made, but it was interesting that they were found there. But yeah, these are, two-dimensional objects, just floating like this. Those are rare, to find because they agglomerate. They are with another thing, or when you have the high pressures in Earth that created minerals, etc., they create typically 3D structures, not two-dimensional structures, atomically thin two-dimensional structures. Yeah. I'm happy to stay here and talk to all of you, okay?
Thank you for coming. Earlier in your talk, you spoke about some of the other families of single atom layer structures.
Yep.
Do these other structures also have the potential for some magic angle? Or is there some inherent property of the crystallographic structure of graphene that allows for this to happen only?
Mm-hmm. That's an excellent question, okay? Let me go back to this slide here. This one. Oh, wait. Yeah, this one is fine. That conical energy momentum relationship, it's very special to graphene, okay? There's no other material that in the bulk of it, there are materials where this thing happens at the edges or on the surfaces, but let's say the material itself, this is almost, exclusive to graphene. There are many other 2D materials, and they have magic ranges, a range of angles over which magic happens, special behavior happens due to interactions and to topology and so on. But in terms of magic angle or magic lines, typically they are the graphene systems, 2, 3, 4, n layers, twisted in symmetric or chiral structures, antisymmetric or chiral structures. So people have studied all of this, the mathematics of this. Typically, it's with graphene systems that you have magic angle, very specific angles where the magic happens. With other materials, it's an extended angular range, which you may think, oh, that's better. I don't have to hit 1.1. I have more tolerance because I have a range of angles. But also, the behavior is, often a little bit less spectacular or was not found as pronounced or as strong as in graphene. So it's good to study, a variety of materials, and see the different properties of the different materials. And we have hundreds of two-dimensional materials, and now everybody's twisting everything on top of each other, to see what happens.
Thank you. So I remind you about tomorrow's colloquium at 3:30 State Laboratory, and you're welcome to come forward and talk to the speaker more. But for now, let's thank Pablo.
Thank you. Thank you all. Please bring me my toys back, You're welcome to try to get one out of me, but bring them back.